All right, so welcome back. We are, say, at the tail end of 1.1, getting ready to start 1.2. There was a problem that I was about to start at the end of the very last video. I've decided to punt on that problem and instead do the following, simply because it serves the same purpose without as much work. So let me go ahead and get started. So reading the question, it reads as follows. It says, determine the values of H such that the matrix is a consistent linear system. Now, do we understand what that question is actually asking? So in order for this matrix to be consistent, a consistent linear system, then it would have to have at least one solution, right? So it says determine the values of H such that the matrix will have at least one solution. You could kind of translate this problem into what values of H, or what can H not be, right? Now, let's go ahead and kind of what I was mentioning at the tail end of that previous video. Having the ability to do row operations on your calculator is extremely beneficial and handy, but your calculator will not know how to row reduce a matrix like this, right? Because again, we have some type of H variable in the matrix. So let's go ahead and what I'm gonna do is, the good news is it's a pretty simple matrix. I'm not gonna have to do a lot of row operations by hand. In fact, I think I only have to do one of them, if I recall. But this is, first off, let's go ahead and establish there's 2 rows, 3 columns. This is a 2 by 3 matrix. And I'm going to just begin by trying to get, I would try to get 1s along the diagonal, and I would try to get a 0 underneath that. So I want to get let's start with trying to get a 0 here. Ready? So the way I would do that, if I want to get a 0, at that entry there, well, I think you can imagine if I were to take -3 multiplied by row sub 1 plus row sub 2. Let's make sure you understand. So -3 multiplied by row sub 1 plus row sub 2. That gives me a new row sub 2. Well, why would do that? Well, because -3 here would cancel the +3 here, right? And I would end up with a 0. So -3 times row sub 1 plus row sub 2 gives me a new row sub 2. And let's go ahead and we'll just go ahead and do that. So -3 times row sub 1, what is that going to equal? Well, let's go ahead and do the math here. So -3. So -3 times 1 is -3, -3 times H, -3 times 4. Okay, and it's going to be plus row sub 2 in just a second. So -3 times row sub 1, it's going to equal -3 minus 3H, and that's going to be -3 times 4, so that's minus 12. Okay, so plus row sub 2. So row sub 2 was 3, 6, 8. So when I finally add these, I end up with 0, and this is basically -3H plus 6. And then finally, -12 plus 8 is -4. Let me rewrite this. So remember, all of this work was to get a new row sub 2. So this, let me try that again. This is going to be inserted here. Row sub 1 doesn't change, right? Row sub 1 still has a 1 and then an H and then a 4. We just used row sub 1 to slightly alter row sub 2. And now we have a 0. And then here, this would be negative 3H plus 6 and negative 4 here. Now, the good news is that's the only row operation that we have to do. And now we're going to take a look at this second row, right? Let's think about that for just a second. So that second row, we have, I'm not going to write the 0. It's just negative 3H plus 6 is equal to negative 4. Okay, so if H is going to cause, right, this H right here, if H is going to cause an inconsistent system, then it's going to come from this statement. Right, if you don't mind, what would an inconsistent system look like? Well, if row 2 were to look like this, 0, 0, negative 4, well, that's a problem. How are you going to add up zeros, right? 0x sub 1 plus 0x sub 2. How are you going to add up a bunch of zeros and arrive at a negative 4? So what I'm trying to say is if any H value that causes me to get a 0 here is going to make this system inconsistent. I'll say that one more time, right? I don't care what H is or is not, but whatever H value causes this to become 0, then I'm left with 0 plus 0 equals negative 4, which makes no sense. So if we just solve, if we, subtract 6 from both sides, and then if we end up just solving the following for H, let's see, what do we get here? So we're gonna solve for H. So H, so actually, let me make sure that I got everything here. Yeah, so what we're gonna do is my apologies for being slightly distracted. I don't want this to be 0, right? So negative 3H plus 6 equals 0. I need to figure out, because if I don't care about this negative 4. I care about, if I get a 0 here, then I have nothing to add up to get to negative 4. So what would H have to be to cause this to become 0? That's the question. All right, well, if we subtract 6 from both sides, we get negative 3H equals negative 6, divide by negative 3, so H equals 2. So here's the problem. If H equals 2, right? If H were to equal 2, then you would have an inconsistent system. If H equals 2, then the second row is the statement 0, 0, negative 4. And that makes no sense, right? That is inconsistent. So let's go back to the question. Because the question was determine the values of H such that the matrix is consistent. We have successfully determined the value of H where it is not consistent. So, well, we just need to simply, it's everything, every other number, right? Every other number except when H is equal to 2. How you can write that, you can write that in interval notation, right? Like here's probably how the book would write it. I'll write it and then I'll translate this. I don't quite know, but I would think that the book probably, if you were to look the answer up in the book, it would probably look something like this. So let me make sure you understand what that means. So you would just read this as the set of all h, or we could say the set of h such that h is a real number where h does not equal, such that h does not equal 2. So it's a set of all numbers, real numbers, such that h does not equal 2. Another way of writing that would be, say, from negative infinity all the way to 2. And then we would union that with 2 to infinity. In other words, you can pick any number for h in this interval, any number of h in this interval. You just can't pick 2. I don't care how you express your answer. That's not that's not the point. The point is, I'm hoping that you understand two things. One is the calculator doesn't quite serve a purpose here. We have to understand our row operations. And second is that we do understand the language. You're being asked about what values would make the matrix consistent. Okay, so these are the values that would make the matrix consistent. This is the value that would make it inconsistent. Okay, so at this stage, we're kind of, we've kind of been going back and forth between 1.1 and 1.2, but this would officially be 1.2. And a lot of the things that are in 1.2 we've already discussed, right? So we've discussed the idea of echelon form, reduced echelon. Now I do want to draw attention to something, because it is different textbooks use different language. So when I was in college, I'll just kind of make sure you understand. There's REF and there's RREF. If you look it up in your calculator, both of these exist in your calculator. Okay? Now, I always learned REF as row echelon form. But your textbook often just calls that echelon form. So your textbook, when they say echelon form, they mean REF. And again, for RREF, I always learned it as reduced row echelon form, where your textbook just calls REF reduced echelon form. Okay? But you can see that, there's that extra R in your calculator for a reason. Reduced row echelon form. Of course, you can read through the difference between REF and RREF right here. It is quite simply, we've already discussed it. RREF gets you right to the answer, whereas REF, you kind of you got to plug things, you got to substitute, solve and substitute and solve and substitute to get to your answer. Okay, now I want to talk a little bit here about again using some language such as pivot. I want to make sure we understand some of this language being used. This theorem here is a uniqueness theorem that basically assures you. Are you ready? Are you ready? So if you use RREF and you get to your answer, and then you were to grab your friend's calculator and take the same matrix and RREF, both of your calculators would look exactly the same. Doesn't matter if it's Casio or Texas Instrument. However, REF, your REF, will depend on which step in the algorithm your calculators did, right? Did they swap, or did they scale, or did they scale before they swapped? So your REF may look different than my REF, which may look different than your friend's REF. But what this means is each matrix is row equivalent to one and only one reduced echelon matrix, meaning each matrix is equivalent to one and only one RREF. Okay, so RREF is always the same answer. Okay, same screen. Okay, now let me see if I can talk to you a little bit about the idea of a pivot, and we'll move into what is a pivot and pivot column, pivot position. But first thing is, what is a pivot? So I don't know if you played sports in in school. It doesn't matter if you did or didn't, but you can imagine, say, like in basketball. After I was good enough to start basketball on my team, but I'm a horrible basketball player, honestly. But after you stop dribbling, right, you can leave one foot planted while you move your other foot around, right? That's called pivoting. So, in other words, you can't double dribble, right? You can't dribble twice, but you can leave one foot planted, and then your other foot, you can kind of pivot your body. That idea translates in matrix form to these positions here. In other words, having ones along this diagonal, okay, having ones there are good positions in which you can pivot. So in other words, if it not only, well, let me read, and then I'll come back to what I was trying to say. So first off, a pivot position in some matrix A is a location in A that corresponds to a leading one in the reduced echelon form of A. That means that will all mean something in just a second. But for now, if you will, just start thinking about ones along that diagonal, okay? Now, a pivot column is quite simply a column that has a pivot in it, all right? A column of A that contains a pivot position. So let me see if I can make sense of this for you. So we start off with matrix A here. And what I'm going to do is I'm just going to I'm going to do some row operations and rewrite matrix A, right? Imagine just, you can REF or RREF, but the idea is quite simply, once you have it in either REF or RREF, you will be able to notice the pivots. So let me see if I can try to highlight them. So for example, this here is a pivot position, right? It's a leading one. Now this 2 is also a pivot position. I agree with you that we would need to get that 2, we would turn that 2 into 1 eventually. But don't you agree that we could get a 1 here, right? We could cut row 2 in half, for example, to get a 1 here. So this is a pivot position. Now, notice that there's no way to get a 1 here, right? Or you could say there's no leading, there's no leading 1 in this third column. So this would be a pivot position if we could get a 1 here, but there's no way you can, there's no way we're going to be able to get a 1 there. So that is not a pivot position. finally, if we go to column, so that's column 1, column 2, column 3. Now we're at column 4. Notice that we could get a 1 here. And that would translate into a pivot position. So what does that mean? So that means that, to answer the question, locate, it says row reduce the matrix A below in echelon form and locate the pivot columns of A. Well, first off, the pivot columns are any columns that have a pivot position. So column 1 has a pivot position. Column 2 has a pivot position. Column 3 does not. Column 4 has a pivot position. There will be no pivot positions for augmented matrices here. Right? This is you got to imagine that you got the that final column is the constants, right? So we can even if this doesn't click yet, I promise you I got a better example on the next page that will help you, okay? But let's actually jump to that. So imagine for just a second, and like I said, if what I just read to you was kind of confusing, bear with me. I promise you after this one, it'll make a lot more sense. So let's imagine that we just got done row reducing echelon form some matrix, right? I don't know what that matrix was, but this is what it looks like after we row reduced. Now, from here, let's see if we can find the pivot columns. Okay. Well, you can see that this is the leftmost. You can have a 1 in the leftmost position here. So that what I just circled is a pivot position. So the pivot columns would equal 1. The first column has a pivot position. Let's you and I agree. Look, here's another. There's another leading 1. So pivot. There's a column 2 also has a pivot position. Notice column 3 doesn't, right? There's no 1 here. In fact, row 3 is just all zeroed out, isn't it? Let me kind of say something that when you see a row, an all zero row. I'm speaking very informally, okay? I just want you should be thinking when you see something like this, like a row 3 where it's all zeroed out, you should be thinking about infinite solutions to that system, okay? But to answer the question, these are the only pivot positions, so therefore these are the only pivot columns. There is no pivot position because, I mean, I'd like, if there was a 1 here, there would, but column 3 does not have a pivot position, so column 3 is not a pivot column. Okay. Now, let me stay here for a second. So I think I can, what I'm going to do, right, because normally what you start off with a system, you turn the system into a matrix, then you RREF the matrix, and now the good news is we can stare at this this matrix and we can normally grab any information we want from it. What I'm going to do is I'm going to go from this matrix back to a system, and I'm doing this for a very particular reason. So, all right. So this, remember, this is x sub 1, this is x sub 2, this is x sub 3. So let's go ahead and translate. We got 1 x sub 1 there's no x sub 2, so it's minus 5x sub 3 is equal to 1. Then when we go to the second row, we have x sub 2 plus x sub 3 is equal to 4. And then when we go to that last row, it's just 0 equals 0, basically. Okay. So do you notice, so here's where I said I think I can try to finally get this to click. Do you notice that that column 3 was not a pivot column? I'll say it again. Stay with me. Column 3 was not a pivot column. It had no pivot position. Notice, now that I'm back into a system, do you notice that equation 1 has an x sub 3 in it, and equation 2 has an x sub 3 in it, right? X sub 3 shows up in both equation 1 and equation 2. I'm going to give that a name in just a second, but that is a way of thinking about pivots and pivot positions and pivot columns. So what we're going to say is the variables are, so I'm going to distinguish between these x variables here and these variables here, right? So here's what I want to be able to say. So any of the variables associated with the pivot columns are what we call basic variables. So basic variables are the variables associated with pivot columns. So in the matrix above, x sub 1 would be a basic variable. X sub 2 would be a basic variable. Now, any variables that are not in pivot columns are what we call free variables. Hopefully this will make sense in just a second. So in our matrix above, x sub 3 would be a free variable, right? So variables not in pivot columns. Okay, so x sub 1, x sub 2, these x sub 1, x sub 2, these are basic variables. X sub 3, we're going to call a free variable. Why this language? Well, because if you solve this system for the basic variables, in other words, let's get x sub 1 by itself. So x sub 1 is going to be equal to, well, let's get that negative 5x sub 3 to the other side. So that's going to be 5, I got a plus, so 5x sub 3 plus 1. And then let's get x sub 2 by itself. So the x sub 2 is going to equal negative x sub 3. What do we got? Plus 4. And then x sub 3 is, well, let me see if I can make sure you understand. So if you solved, do you now agree, once you've solved this system for the basic variables, this, I'm going to say it slow, this system is represented in terms of the free variables. What I'm trying to say is, if you say, hey, what's x sub 1? I'm going to turn to you and say, well, it depends on what x sub 3 is, right? You got to give me an x sub 3 before I can give you an x sub 1. You got to give me an x sub 3 before I can give you an x sub 2. So when you have free variables, First off, free variables typically mean well, let me not speak matter-of-factly. Let's think infinite free variables. Let's be thinking infinite solutions. Okay? All right. So what we're going to do, what I want to do now is I want to show you how you express your solutions. In other words, I've gotten pretty far in this process. There's one more step that I have to do here. But before, let me see here. Yeah, let me go ahead and do it with this problem just for the sake of time. So, okay, I'm gonna give myself a little bit of space, get rid of this definition, the basic variable. I'm gonna get rid of this definition of free variables. And we'll take a break in just a second. So are you following me that we went from the matrix back to the system, and then all we did was take this system and solve it for your basic variables. What we're going to do now is we're going to write x sub 3 is free. Okay. So what you now have is the parametric representation of your solution. Or what, yeah, so I'll go ahead and write that. So often you're going to hear this referred to as the general solution to a system, or the parametric representation of the solution, parametric description. This is just two ways of saying the same thing, that in other words, once you solve your system, once you get here, your REF, you're going to be asked to now write your answer or express the result as a general solution to the system. And this is what they want when they ask for the general solution. So in this case, you now can give this to your client, and your client knows that they are free to pick whatever they want for variable x sub 3. But once they have chosen x sub 3, the other two variables are determined by the choice of x sub 3, right? So x sub 3 is an independent variable. You can choose whatever you want. That's why we say it's free. It's free. It's a free variable. You're free to choose whatever you want to plug in for x sub 3. Your other variables, your basic variables, depend on what you choose for x sub 3. So they are in terms of your free variables. One more time, basic variables are always represented in terms of free variables. I shouldn't use the word always there, but I think it's it'll serve for now. All right, so we will reconvene, and I promise there's some really cool stuff you can do with linear algebra, but we got to get there. So stay with me. See you in the next video.